the direction in which the variance is higher.
Can you say it again?
I mean, you select direction in which the variance is higher, the unit vector.
Well, I want it to be the same in all directions. It should be completely random. It should be equally likely in every direction. Right. So one simple idea is, okay, I can generate a random value in a box, right? I can pick two random. So the operation we typically have for ourselves is we can pick a value, let's call this S, which is uniform random in 0, 1. Right? So it gives us a value between 0 and 1 at random. I do that twice. I get two coordinates, and I get a point, and then I take this point, and I'm going to, this is not a unit vector, but then I can normalize it, and it becomes a unit vector. Well, this doesn't work. This is wrong, and in high dimensions, it's really wrong. These corners have more mass here. These directions are more likely to get chosen than this direction. And in high dimensions, this gets even worse. So I'll kind of go through I'll illustrate this a bit more in another lecture. So this idea doesn't work, but I can pick this uniform random number. In fact, I can pick two of these, say T and S. In fact, in order to generate one, I'm going to need two uniform random values. Luckily, I can actually get two Gaussian random variables out of it. So, or I can get two. So, what I can do is I can do what's called a Box-Mueller transform. And so this Box-Mueller transform, what it does is it goes from two uniform 0, 1 random variables, and it generates two Gaussian random variables.
How about generating a point in radial coordinates and then converting it to this?
Okay, so this Box-Mueller transform is kind of doing that.
Okay.
I've seen a paper that tried to work out that math at some point, and it's kind of messy, and the higher dimensions you go, it gets crazier and crazier. They worked it out for 3 dimensions. That's the harder way to do it. So you can get, from two uniform random variables, you can get two Gaussian random variables. And Gaussian random variables have the nice property that a uniform Gaussian, it's going to be, if you have a multivariate Gaussian random variable, each dimension looks like a Gaussian independent of what the other value is. So you can generate two of these, or you can get D of these, and then you create a D-dimensional Gaussian random variable, and then you normalize it. Okay, so you do this D over 2 times, and you get D Gaussian random variables. So G1, G2, GD, which is a single D-dimensional Gaussian, and then you normalize, and you get U, which is uniform in SD minus 1. Sorry, I ran out of space. So you need to use this Box-Mueller transform, and I've got 1 minute left, so I'll write this up. It's a bit. So I'm going to generate two Gaussian random variables, and I'll just write down for one of them. The other one is similar. So it's square root of -2 natural log of s, which is one of your uniform random variables, times the cosine 2 pi of t, which is the other random variable. You can get the second one as the same times the sine. And these are going to be two independent Gaussian variables. So this transformer property is pretty amazing. So it turns out you can do this for Gaussian random variables, and that works for for a locality sensitive hash function for the Euclidean distance using this projection and binning operation. If you want to do something like the L1 distance, the Manhattan distance, you can do something similar, but you can't use Gaussian random variables. Instead, you need to use something like what's called a Cauchy random variable. And maybe on Monday we'll talk a bit more about this.